Welcome back. In this video, we're going to look at some example problems of using the shell method to calculate the volume of solids of revolution. Let's get to it. Alright, so here's our first example. We want to find the volume of the solid that results from revolving the region enclosed by y equals 1 divided by x, y equals 0, x equals 1, and x equals 3 around the y-axis by using cylindrical shells. Alright, and so the first thing that I always recommend that you do when you're working on a problem like this is to graph everything that you've been given. And so if we start by drawing our coordinate plane, I'll begin by drawing the y-axis, and then we will draw the x-axis, and then I'll label them. So this is the y, and this is the x. And so there we go. And now, let's graph each of our equations. First, we have y equals 1 divided by x. And the graph of 1 divided by x has an asymptote at the y-axis and at the x-axis. And so it looks a little bit like this. We'll have a curve like that, and we'll have a curve like that. Okay, so that's going to be y equals 1 divided by x. Then our next line is y equals 0, and y equals 0 is just the x-axis, right? That is where y is equal to 0. So remember that that is going to be one of the boundaries of our region. Then our next line is x equals 1, and so if this is x equals 1, then our line for x equals 1 will look like this. All right, so that will be x equals 1. And then our last line is x equals 3, and so if this was x equals 1, then we'll say that this is x equals 3, and our line for x equals 3 will look like this. All right, and so that is x equals 3. And so now we can see that the region that is bounded by all of those graphs will be this region right here. It is bounded at the bottom by the x-axis, or y equals 0, and then x equals 1, 1 divided by x, and x equals 3 create the other boundaries of that region. All right, and so I'll shade this region in, and we're going to be revolving this region around the y-axis. And so I'm going to draw a little arrow around the y-axis so we remember what axis we are revolving around. All right, so now that we have graphed everything that we've been given, we are ready to set up a definite integral to represent the volume of the solid formed by revolving this region around the y-axis using the shell method. And so since we're revolving around the y-axis, which is a vertical axis of revolution, we are going to be working in terms of x for the shell method. And the formula for working in terms of x for the shell method looks like this. We have that the volume is equal to 2 pi times the integral from a to b, which are two values of x, of the radius in terms of x times the height in terms of x, and that is multiplied by dx. Now the radius and the height are referring to the radius and the height of our cylindrical shells that we are using to calculate the volume of the solid of revolution. And so if we take a look at a small rectangular region of the region that we are revolving around the y-axis, and that rectangle is parallel to the axis of revolution, and you were to revolve that rectangle around the y-axis, that would form a cylindrical shell. So the radius, r of x, for that shell will be the distance from the y-axis, or the axis of revolution, to that rectangle. Now in this case, since we're working in terms of x, that radius is just going to be equal to x, because no matter where we draw this rectangle, the distance from the y-axis to that rectangle is just going to be whatever value of x our rectangle is located at. And so we know that r of x is equal to x, but what about the height, h of x? Well, the height corresponds to the height of our cylindrical shells, which corresponds to the height of our rectangle. And the height of the rectangle is the distance from the x-axis to this curve right here, 1 divided by x. And that distance is just going to be this function, 1 divided by x, right? The height of the rectangle is dependent on the y value of this function, which is equal to 1 divided by x. And so our height in terms of x is equal to 1 divided by x. Now the only other thing that we need to set up this definite integral is to determine our bounds of integration, or the values of x that our region lies between, which we can clearly see from this graph is between x equals 1 and x equals 3. And so the volume will be equal to 2 pi times the integral from 1 to 3 of the radius x times the height 1 divided by x times dx. All right, so this definite integral represents the volume of the solid of revolution formed by revolving this region around the y-axis using cylindrical shells, or the shell method. And so now all we have to do to find that volume is to solve this definite integral. And so note that x times 1 divided by x is just going to be equal to 1, right? We're going to have x divided by x, and anything divided by itself is 1. And so really we have that this is equal to 2 pi times the integral from 1 to 3 of 1 times dx. And so if we clean up our work, we can integrate 1, and that's just going to be x, right? When you integrate a constant, you just multiply it by the variable of integration, which in this case is x. And so we will have that this is equal to 2 pi times x evaluated from 1 to 3. And this is pretty simple. Now we just plug in 3 and then subtract plugging in 1. So we're just going to have 3 minus 1. So this is equal to 2 pi times 3 minus 1. And 3 minus 1 is equal to 2. And so this is equal to 2 pi times 2, which is equal to 4 pi. And so 4 pi is the volume of the solid of revolution formed by revolving this region around the y-axis. So for our next example, we want to find the volume of the solid that results from revolving the region enclosed by y equals x cubed, x equals 0, and y equals 8 around the x-axis by using cylindrical shells. Okay, so once again, the first thing that you should do here is graph everything that you've been given. And so you want to draw a coordinate plane, and I'll start by drawing the y-axis, and then I'll draw the x-axis, and then I'll label it. So this is the y-axis, and this is the x-axis. And then let's graph y equals x cubed, and we know that the graph of an x cubed function will look something like this, and so that will be y equals x cubed. And then next we have x equals 0, and x equals 0 is just the y-axis, right? That is where x is equal to 0. And so we don't really need to redraw that line. Just remember that that is going to be one of our boundaries. And then we have y equals 8, which if y equals 8 is right there, then this line would represent y equals 8. Okay, so that is y equals 8. And so now we can see that the region that is enclosed by the y-axis, y equals 8, and x cubed, is this region in here. And so I'll shade that region in. This is going to be the region that we are revolving around the x-axis to form a solid of revolution. And so since we are revolving around the x-axis, I also want to make a note of that. And so I'll draw an arrow around the x-axis so we remember what axis we are revolving around. Okay, and so now that we have graphed everything that we have been given, we are ready to set up a definite integral to represent the volume of our solid of revolution. And so since we're using the shell method and we are revolving around the x-axis, which is a horizontal axis of revolution, we are going to be working in terms of y. And so we will be using the following formula for the shell method. We will have that the volume is equal to 2 pi times the integral from c to d, which are values of y, of the radius in terms of y times the height in terms of y times dy. All right, and the radius is still the radius of our cylindrical shells, and the height is still the height of our cylindrical shells. And so if we look at a small rectangular region that is parallel to our axis of revolution and will represent one cylindrical shell that would be formed by revolving that region around the x-axis, the radius of that cylindrical shell will be the distance from the x-axis, or our axis of revolution, to wherever our rectangle is. And so that is going to just be y, right? The distance between our axis of revolution and wherever our rectangle is will be a value of y along the y-axis. And so r of y, the radius, is equal to y, and that's always going to be the case if you're working in terms of y and you're revolving around the x-axis. Your radius will always be y, just like it will always be x if you're revolving around the y-axis, like we saw in our previous example. But then how about the height? What would h of y be equal to? Well, the height would be equal to the height of our rectangle, which is equal to the distance from the y-axis to this function right here. Okay, so if this distance was the radius, then this distance is the height. And that distance is the function x cubed, right? The height of this rectangle is entirely dependent on this function. However, that height needs to be in terms of y, and so we need to get this equation in terms of y by solving for x, right? It would be incorrect to say that the height is equal to x cubed because that's not in terms of y, and we need to set up our definite integral in terms of y in order to calculate the volume. So x cubed is not correct. We need to solve for x here by taking the cubed root of both sides of the equation, and that will give us that x is equal to the cubed root of y. And so the height in terms of y for our rectangles and ultimately our cylindrical shells will be the cubed root of y. Okay, and so now that we have our radius and our height, all we need to determine now is what two values of y our region lies between, right? What are going to be the bounds of our integral? And so in this case, our region lies between y equals 0 and y equals 8. And so our definite integral will look like this. The volume will be equal to 2 pi times the integral from 0 to 8 of the radius y times the height, the cubed root of y. And then we will multiply by dy. Okay, and so this definite integral represents the volume of the solid of revolution formed by revolving this region around the x-axis. All right, and so this definite integral represents the volume of the solid of revolution formed by revolving this region around the x-axis using cylindrical shells. Okay, and so now all we have to do to find that volume is to simplify and solve this definite integral. And so let's do that. Note that the cubed root of y can be rewritten to be y to the 1/3 power. And so we'll have that this is equal to 2 pi times the integral from 0 to 8 of y times y to the 1/3 power times dy. And then if we're multiplying y to the first power times y to the 1/3 power, we can add their exponents. And so 1 plus 1/3 is equal to 4/3. And so we can rewrite this integral to be y to the 4/3 power times dy. Okay, and so now if we clean up our work, we can integrate this term by using the power rule of integration. So this will be equal to 2 pi times the integral of y to the 4/3 power. And so to integrate that, we will add 1 to the exponent and then divide by that new exponent. Now 4/3 plus 1 is 7/3, and so we will have y to the 7/3 power, and then we will divide by that new exponent, which is 7/3, and that will be evaluated from 0 to 8. Now when you divide by a fraction like 7/3, that is essentially the same as multiplying by the reciprocal of that fraction, and so this would be equal to 2 pi times 3/7 times y to the 7/3 power, evaluated from 0 to 8. Okay, so we just flip the numerator and denominator to get the reciprocal, and we multiply it by our term, and this is equivalent to this expression. Okay, and so let's clean up our work again, and now we can evaluate this at 8 and subtract the evaluation at 0. And so this will be equal to 2 pi times 3/7 times 8 to the 7/3 power minus 3/7 times 0 to the 7/3 power. Now 0 to the 7/3 power is just 0, and so 0 times 3/7 is also 0, and so we're just subtracting 0, so we don't really need to write that. That's not going to affect our calculation. But then we have this funky 8 to the 7/3 power that we have to calculate. Now you can plug this into your calculator, and that will give you 128. But if you want to do it by hand, what you can do is rewrite 8 to be 2 cubed, because 2 times itself 3 times is 8. And so if you do that, you'll have that this is equal to 2 pi times 3/7 times 2 cubed to the 7/3 power. And now if you multiply these exponents together, those 3's will cancel out, and so you'll just be left with 2 to the 7th power. Right, so what happens is this will be equal to 2 pi times 3 divided by 7 times 2 to the 3 times 7/3 power, but these 3's cancel out, and so we just have 2 to the 7th power. And so I'll just rewrite that as 2 to the 7th power, and 2 times itself 7 times is 128. And so if we clean up our work again, we will have that this is equal to 2 pi times 3 divided by 7 times 128, and 2 times 3 is 6, times 128 is 768, and so our final answer is that this is equal to 768 pi divided by 7. And this cannot be reduced any further, and so that is going to be our final answer. This is the volume of the solid of revolution formed by revolving this region around the x-axis. All right, so here's our next example. We want to find the volume of the solid that results from revolving the region enclosed by y equals 2x minus 1, y equals negative 2x plus 3, and x equals 2 around the y-axis by using cylindrical shells. All right, and so just like in our previous examples, the first thing that we should do is draw a graph of everything that we've been given. And so I'll start by drawing the y-axis, and then I'll draw the x-axis, and then I'll label them. So this is the y-axis, this is the x-axis, and then we can graph all of our lines. So first up, we have y equals 2x minus 1. We know that this is going to be a linear function, or a line with a slope of 2 and a y-intercept of negative 1. And so if this is y equals negative 1, and this is y equals positive 1, and this is x equals positive 1, then our line would look something like this. All right, so this will be the line y equals 2x minus 1. And that is because it has a slope of 2, so it increases 2 units and then moves over 1, and it has that y-intercept at negative 1. Okay, and then our next line is y equals negative 2x plus 3, and so this is also a linear function that has a slope of negative 2 and a y-intercept of positive 3. So if this is y equals positive 2, and this is y equals positive 3, then our line will look something like this. Okay, so that is going to be our line y equals negative 2x plus 3. It has that y-intercept of 3 and a slope of negative 2, so it moves down 2 units and then over 1 unit. And now we can see that these two functions actually intersect at 1, 1, and so I'll label that intersection point. That is the point 1, 1, and so that might come in handy later on. All right, and then finally we have the line x equals 2, and so if this is x equals 2, then this line will represent x equals 2. So that is going to be x equals 2. And so now we can see that the region that is bounded by these 3 lines will be this triangular region right here. And so I'll shade that in. This is going to be the region that we revolve around the y-axis to form a solid of revolution. Okay, and so since we are revolving around the y-axis, right, that's what our problem tells us, I also want to make a note of that, and so I'll draw an arrow around the y-axis so we remember which axis we are revolving around. And so now that we have graphed everything that we've been given, we are now ready to set up a definite integral that will allow us to calculate the volume of the solid of revolution formed by revolving this region around the y-axis. And so since we are revolving around the y-axis, that means that we are going to be working in terms of x for the shell method. And so we are going to use the following formula, that the volume is equal to 2 pi times the integral from a to b, which are 2 values of x, of the radius in terms of x times the height in terms of x times dx. Okay, and so if we're going to determine the radius and the height, let's draw a rectangle in our region to represent one of the cylindrical shells. And remember that that rectangle needs to be parallel to the axis of revolution. Okay, and so this is parallel to the y-axis. And so if we start with the radius will be equal to the distance from the axis of revolution to our rectangle. And in this case, that's just going to be equal to x, right? The distance between this axis and whatever rectangle we draw throughout this region will be some value of x along the x-axis. It's all dependent on where we draw that rectangle. And so we can represent that with x, and so r of x is equal to x. All right, but then what about the height? What about h of x? What will that be equal to? Well, if we look at our rectangle, the height is dependent on this line and this line, right? The distance between these two lines is going to determine the height of each cylindrical shell or of each rectangle. And so we need to subtract this bottom function from this top function to find that distance or that height. And so our height will be equal to 2x minus 1 minus negative 2x plus 3. So we will have 2x minus 1 minus negative 2x plus 3. And remember to put that in parentheses because if you don't, this negative won't be distributed to both terms and you will get an incorrect height. You need to subtract that entire function. And so if we simplify, this will be equal to 2x minus 1. And then if we distribute this negative through this quantity, we will have positive 2x because these two negatives will cancel out, and then we will have minus 3. Okay, and so then we can combine like terms. We have two 2x's that will combine to become 4x, and then we have a negative 1 and negative 3 that will combine to be negative 4. And so the height will be equal to 4x minus 4. Okay, and so now that we have the radius and the height for the cylindrical shells in this scenario, now all we need to determine to set up our definite integral are the bounds of integration, right? What two values of x does our region lie between? And in this case, we can see that it lies between x equals 1 and x equals 2. And so if we clean up our work here, we will have that the volume is equal to 2 pi times the integral from 1 to 2 of the radius, which is x, times the height, 4x minus 4, times dx. All right, and so this definite integral represents the volume of the solid of revolution formed by revolving this triangular region around the y-axis using cylindrical shells. And so now all we have to do to find that volume is solve this definite integral. And so if we distribute this x through this quantity, we will have that the volume is equal to 2 pi times the integral from 1 to 2 of 4x squared minus 4x times dx. And so if we clean up our work, we can simplify this a little further by pulling out a common factor of 4 from each of these terms. So if I pull that 4 to the outside of the integral and multiply it by 2 pi, that will be equal to 8 pi times the integral from 1 to 2 of x squared minus x times dx. And that's going to be a little simpler to work with, right? We just pulled out that common factor of 4 to the outside of the integral and multiplied it by 2 pi to get 8 pi. Okay, and so now we can integrate using the power rule of integration on x squared and negative x. And if we do that, we will have that this is equal to 8 pi times x to the third power divided by 3 minus x squared divided by 2, and that will be evaluated from 1 to 2. Okay, so we added 1 to the exponent of x squared and got x cubed, and then divided by that new exponent of 3, and then we added 1 to this exponent to get x squared, and then divided by that new exponent of 2. And so if we clean up our work again, we can evaluate this expression at 2 and then subtract evaluating 1 for this expression. And so this will be equal to 8 pi times 2 cubed divided by 3 minus 2 squared divided by 2 minus 1 cubed divided by 3 minus 1 squared divided by 2. Okay? And so if we simplify, this is equal to 8 pi times 2 cubed, which is 8 divided by 3, minus 4 divided by 2 minus 1/3 minus 1/2. And so if we simplify again, this will be equal to 8 pi times 8/3 minus 2, and then we will subtract 1/3 minus 1/2, and 1/3 minus 1/2 is equal to negative 1/6, and so we'll have negative 1/6. And then if we clean up our work again, this will be equal to 8 pi times 8 divided by 3 minus 2 plus 1/6, since those negatives will cancel out. And then we can simplify a little bit more. We can rewrite negative 2 to be negative 6/3. And if you subtract 6/3 from 8/3, you'll be left with 2/3. And so this is equal to 8 pi times 2/3 plus 1/6. And 2/3 is the same as 4/6. And so if you add 4/6 to 1/6, then you have 5/6. And so this is equal to 8 pi times 5/6, and that is equal to 40 pi divided by 6, which can be reduced by a factor of 2 to be equal to 20 pi divided by 3. And so that is the volume of the solid of revolution formed by revolving this region around the y-axis. All right, so here's our final example. We want to set up a definite integral that represents the volume by using cylindrical shells of the solid that results from revolving the region bounded by y equals x cubed, x equals 2, and y equals 0 around the following lines. And so we have 4 lines here that are not the x or y axis that we are going to revolve around. And so when we revolve around lines that are not the x or y axis, and we're using the shell method, we have to adjust our radius to account for where that axis of revolution lies. And so that can be a little bit tricky, but thankfully I have some rules that we can follow to make this a lot more simple. And so I've already gone over these rules in my lesson video on this topic, but I'll go over them again as it's going to be very convenient for us to be reminded of them as we go through this example problem. And so here are the rules you need to know. If you are revolving around a vertical axis, which means you're going to be working in terms of x, and your region is to the left of the axis of revolution, like it is right here, it's to the left of this axis, then you will subtract the radius, which would be x, from the axis value. So if this line right here was x equals 5, the radius in this example would be 5 minus x. We would subtract the radius from the value of that axis. If our region is to the right of the axis of revolution, like it is in this picture, then we will subtract the axis value from the radius, which is x. So if this line right here is y equals negative 2, then we would subtract negative 2 from x, and that would be our radius. So we would have x minus -2, which would be x plus 2. All right, so those are the two rules when you're working in terms of x or you're revolving around a vertical axis. But if you're revolving around a horizontal axis, meaning that you are working in terms of y, and your region is below the axis of revolution, then you want to subtract the radius, which would be y in this case, from the axis value. So if this line right here was y equals 2, then your radius would be 2 minus y. You would subtract y from the value of that line. But if your region is above the axis of revolution, then you want to subtract the axis value from the radius, which would be y. So if this line right here was y equals -1, then our radius would be y minus -1, and so that would be y plus 1. All right, so those are both of the rules when you're revolving around a horizontal axis. All right, and so to summarize, whatever is on the top when you're working with a horizontal axis, so if the axis is on top or if the region is on top, you're going to subtract whatever is below it. So in this case, since the line is above the region, we subtract the radius from the value of the line. And in this case, since the region is above the line, we subtract the value of the line from the radius. And that same principle holds true over here, except you're looking from right to left. So whatever is on the right side, you subtract what is on the left from that. So if your axis of revolution is on the right, then you subtract the radius from the value of that line. But if your region is on the right side, then you subtract the value of the line from your radius. Okay, so that's the simple way to think about it, but you can always read through these rules if you're not sure. But to go back to our example problem, before we start looking at these different lines as our axis of revolution, we first need to graph everything that we've been given. And so let's start by drawing the coordinate plane. And so here's the y-axis, and here's the x-axis, and then I'll label them. So this will be the y-axis, and this is the x-axis. And then let's graph everything we've been given. So let's start with y equals x cubed. If this is x equals 1, and this is y equals 1, then y equals x cubed will look something like this. All right, so it's not perfect, but that is going to be y equals x cubed. The important feature to get right is that it crosses through the origin, and it has the coordinate point 1, 1, and -1, -1. And so just as a reference, this is x equals -1, and this is y equals -1. Okay, and then next we have the line x equals 2, and so this will be x equals 2, and so that line will look something like this. That is going to be x equals 2. And then our last line is y equals 0, which is just the x-axis because that is where y is equal to 0. Okay, and so now we can see that the region that is bounded by the x-axis, x equals 2, and y equals x cubed, is this region in here. And so I'll shade that in. This is the region that we are going to be revolving around those different lines that are not the x or y axis. All right, and so let's start with part A with the line y equals -1. Y equals -1 is located down here, and so that line will look something like this. That is going to be the line y equals -1. And so if we're going to revolve this region around this line, note that this line is a horizontal axis, and it is parallel to the x-axis, which means that we are going to be working in terms of y for the shell method. And so for part A, we are going to be looking for the radius in terms of y, and we are going to be looking for the height in terms of y. And so let's start with the radius, but first we need to draw our representative rectangle for our region that represents one of the cylindrical shells that would be formed. And remember that that rectangle needs to be parallel to the axis of revolution, so it will look something like this, and you can put it anywhere within this region. I just chose to put it right here. And so the radius is going to be equal to the distance from this line, the axis of revolution, y equals -1, and wherever that rectangle is drawn. And so normally, when we're working in terms of y, that would just be equal to y. But since we're not revolving around the x-axis, we need to adjust that radius. Okay, and so since our region is above that axis of revolution, we will subtract the value of that line from our radius, which would be y. So, since our line is y equals -1, our radius will be equal to y minus -1. And so that is equal to y plus 1. And so that is the radius, or the distance, from that axis to our rectangles. Okay, and so then for the height, that is going to be the height of our rectangle, which would be the height of our cylindrical shells, and that is going to be equal to the distance between x cubed and x equals 2, right? This height of this rectangle is the distance between these two lines. And so if we subtract the left boundary from the right boundary, we will have that distance. Okay, and so the height will be equal to 2 minus x cubed. However, remember that our height needs to be in terms of y, and so we need to get this equation in terms of y. And so if we solve for x by taking the cubed root of both sides, that will give us that x is equal to the cubed root of y. And so our height will be equal to 2 minus the cubed root of y, right? The right boundary minus the left boundary. And so now that we have the radius and the height, we can set up our definite integral to represent the volume of the solid of revolution formed by revolving this region around the line y equals -1 by using the shell method. Okay, and so we will have that the volume is equal to 2 pi times the integral, and then our bounds of integration need to be values of y since we are working in terms of y. And so, what two values of y does this region lie between? Well, we know the lower bound is y equals 0, but what about the upper bound? It looks like that's going to be where this function and this line intersect. And so all we have to do to determine that is plug x equals 2 into this function. And so if x equals 2, we have 2 cubed, and 2 cubed is equal to 8. So the y value right here at that intersection point is y equals 8. And so I'll label that. There's y equals 8. And so that means that our upper bound will be 8. So our region lies between y equals 0 and y equals 8. And so then we have a radius, y plus 1, times the height, 2 minus the cube root of y, times dy. And so this is the definite integral that represents the volume of the solid of revolution formed by revolving this region around this line, y equals -1, by using the shell method. Okay, so let's clean up our work, and then we will look at the next line that we are going to revolve around. And so our next line is y equals 8, and so y equals 8 is right here, and so that line will look like this. This will be the line y equals 8, so I will label that. There is y equals 8. And so once again, if we're going to revolve around this line, if this is our axis of revolution, then we are going to be working in terms of y because that line is parallel to the x-axis, right? When we have a horizontal axis of revolution, we work in terms of y when we use the shell method. So for part B, we're going to be looking for the radius in terms of y and the height in terms of y. In this case, we're going to be using that same representative rectangle, right? That's still going to be parallel to our axis of revolution. And so in this case, the radius will be y, but we need to adjust it based on where our region is in relation to our axis of revolution. Now, since our axis is above the region, we are going to subtract the radius, y, from the value of the axis. And now in this case, that value is 8, and so our radius will be equal to 8 minus y. Okay, and then for the height is actually going to be the same as it was for part A. The height is not affected by where your axis of revolution is. So the height is still going to be equal to the distance between these two boundaries, which will be 2 minus the cube root of y. And so we will have 2 minus the cube root of y. Right, we have the right boundary minus the left boundary. Okay, and so now once again, we are ready to set up our definite integral. We will have that the volume is equal to 2 pi times the integral, and then our bounds of integration are going to be the same as they were for part A, since we're still working in terms of y. Our region still lies between y equals 0 and y equals 8, and so our bounds will be from 0 to 8, and then we will have our radius, 8 minus y, times the height, 2 minus the cube root of y, times dy. And so this definite integral represents the volume of the solid of revolution formed by revolving this region around the line y equals 8 by using cylindrical shells, or the shell method. Okay, so let's clean up our work, and then we will look at our next axis of revolution. All right, so now we're on to part C, where we're going to look at x equals -2. And x equals -2 is located right here on the x-axis, and so I'll label that. There's -2. And so the line x equals -2 will be right here. All right, so that is going to be x equals -2. And so if we're going to revolve around this line, if this is our axis of revolution, then we are going to be working in terms of x because this is a vertical axis of revolution and it is parallel to the y-axis. Okay, so we're going to be working in terms of x, which means that for part C, we are going to want a radius in terms of x and a height in terms of x. But before we can determine the radius or the height, we first need to draw a new representative rectangle since we are revolving around a vertical axis. Okay, so our rectangle needs to be parallel to that axis. And so now the rectangle will look something like this, where the distance between that axis of revolution and that rectangle will be our radius. Now that radius would normally be x, but since we are revolving around a vertical axis that is not the y-axis, we need to adjust that radius. And that is dependent on where our region is in relation to that axis of revolution. And so, since our region is to the right of that axis, we want to subtract the value of the axis from our radius, which is x. And so the value of our line is -2, which means that we will have that the radius is equal to x minus -2, which is equal to x plus 2. All right, and then the height is going to be equal to the height of the rectangle, and the height of the rectangle is the distance between the x-axis and this function right here, y equals x cubed. And so that distance will be equal to that function, right? The height of this rectangle depends on where you are along this function. And so x cubed is going to be our height in terms of x. That will be equal to x cubed. All right, and so now that we have the radius and the height, we can set up our definite integral. We will have that the volume is equal to 2 pi times the integral. And now our bounds of integration need to be values of x, since we are working in terms of x. And so we need to know what two values of x does our region lie between. Well, it looks like it's going to be x equals 0 and x equals 2. And so our bounds of integration will be 0 to 2. And then we'll have our radius, x plus 2, times the height, x cubed, times dx. And that is the definite integral that represents the volume of the solid of revolution formed by revolving this region around the line x equals -2 using cylindrical shells or the shell method. Okay, and so let's clean up our work one more time, and we will take a look at part D, which will be our last axis of revolution. Okay, so finally we're going to look at the line x equals 2. That's going to be our new axis of revolution. And note that x equals 2 has already been graphed right here. So this line, x equals 2, I'm going to circle that. That is our new axis of revolution. And so since that axis of revolution is vertical and it's parallel to the y-axis, we are going to be working in terms of x once again. So for part D, we are looking for a radius in terms of x, and we're looking for the height in terms of x. And so let's start with the radius. The radius would normally be x, but since we're not revolving around the y-axis, we need to adjust that. And that is based on where our region is in relation to that axis of revolution. Now our region is to the left of the axis, and so that means we are going to subtract x from the value of our axis of revolution. In this case, that is 2, and so our radius will be equal to 2 minus x. Okay, so that is going to be the radius, or the distance between the axis of revolution and our rectangles that we would use to form the cylindrical shells that would form our solid of revolution. Now the height in terms of x is going to be the same as it was for our previous line. It's still going to be equal to x cubed because that is the height of the rectangle, or the distance from the x-axis to this function, which is x cubed. Okay, and so now we can set up our definite integral. We will have that the volume is equal to 2 pi times the integral with our bounds of integration in terms of x, which our region still lies between x equals 0 and x equals 2, and so our bounds will be from 0 to 2, and then we will have our radius, 2 minus x, times the height, x cubed, times dx. And so that represents the volume of the solid of revolution formed by revolving this region around the line x equals 2 by using cylindrical shells. Okay, and so with that, that is the end of this example, and this was the last example for this video. So if you have any questions, feel free to leave those in the comments, but if you don't have any questions, this is all I had for now, so I will see you next time.